Dear friends, I hope you have enjoyed my lecture on magnetic field. Today, I want to discuss with you about Biot-Savart law and its application. I already introduced what is Biot-Savart law and what is its origin. Now, according to Biot-Savart law, the magnetic field due to a current element IDL at a field point P, which is at a distance r, can be written as mu0 by 4 pi IDL cross r hat divided by r square. Now, one thing you should remember that this magnetic field B is perpendicular to the plane which contains the current element IDL and the field point P. So I can write it also as mu0 by 4 pi IDL cross R2 minus R1 divided by mod of R2 minus R1 cube. I just replaced the unit vector R hat by a vector R2 minus R1. Therefore, as a first example, I want to derive the magnetic field due to a straight current carrying wire. I am just drawing a simple figure here. I am considering the field point is along y-axis. Say it is the field point P, which is at a distance a from the x-axis, and the current element extends from minus infinity to plus infinity, and a constant current flows through, and a constant current I flows through this wire. So at first I will consider a current element IDL. The distance of the field point P from this current element is R2 minus R1, and the current element is at a distance x from the origin O. Now, for the sake of my problem, I consider that R2 minus R1 makes an angle theta with the x-axis as shown in the figure. Now, from the geometry, I can write B at the point of R2, that is at P equals to mu0 by 4 pi into I integration minus infinity to plus infinity, because the current extends from minus infinity to plus infinity, dx into I hat, here dl is equals to dx, cross R2 minus R1 divided by mod of R2 minus R1 cube. Since R2 minus R1 is on the xy plane, the magnetic field will be along k hat. Mind it, magnetic field will be along k hat. It is obvious. Now, for this problem, you can see from the figure that I hat cross R2 minus R1, that is equals to R2 minus R1 mod into sine theta into k hat, and further a by x equals to tan pi minus theta. So x is equals to minus cot theta, and dx is equals to minus a cot theta, and dx equals to a cosec square theta d theta. and R2 minus R1 equals to R2 minus R1 mod equals to A cosec theta. Therefore, if I replace the value of dx R2 minus R1 and also I hat cross R2 minus R1, then I can find B at R2 is equals to mu 0 by 4 pi into I into k hat into 1 by a integration 0 to pi sine theta d theta is equals to mu 0 by 4 pi by into I divided by a into k hat. The result of this integration is cos theta 0 to pi, that is equals to mu 0 I by 2 pi a into k hat. So the magnetic field is mu 0 I by 2 pi a into k hat, where a is the distance of the field point from the x-axis. Now you have already did this calculation in your 10 plus 2 level, but just observe that here we have approached the problem completely vector notation. So as we are in undergraduate level, you must start the problem vectorially. Now as a second example, I want to find out the magnetic field due to a circular loop. Here also the current flowing through this loop is a constant, that is I. Now also I am drawing a simple figure. I am considering, for the sake of simplicity of the problem, that the field point is along the axis of the circle. Say it is the z-axis. This is x, this is y, and this is z. Now here is the set field point P, and the current flowing through this circular loop is I. So here also we will consider a current element IDL. From the current element, the field point is at a distance R2 minus R1. I am considering the same approach. Now this current element makes an angle theta with the x-axis. Therefore, from the symmetry, I can write that I am just writing first dB is equals to mu 0 by 4 pi I dl cross r hat divided by r square here. Now I will replace dl r square by and I dl r square etc. as per our figure. Now from this figure you can remember that dl, what is the value of dl? Just observe that. Now I am to write the expression of dl. I just draw a figure. Say this is x, this is y, and from this figure you can remember that the dl is along this direction. So this is the direction of dl. I can vectorially find its components along x and y axis. So I can write as per the figure that dl is equals to minus a sine theta plus dl is equals to minus I hat a sine theta minus a sine theta into plus j hat a cos theta d theta. I'm just as magnitude mod of dl is equals to a into d theta. I am just making components along x-axis and along y-axis. Now, as per the figure, R2 minus R1, that is equals to, say, if the origin is at is O and the current element is at S, so I can write R2 minus R1 is equals to K hat Z. R2 minus R1 is equals to K hat Z minus OS. So, what would be the value of R2 minus R1? That would be K hat Z minus I hat A cos theta minus J hat A sin theta. Therefore, the value of mod R2 minus R1 as per our figure, you can see it will be equals to root over of a square plus z square. Substituting all these results on B, obviously it is along k hat direction, is equals to mu 0 I by 4 pi integration 0 to 2 pi. Now, to complete the circle, I have to move. You can remember that we have find this is ideal and this was x-axis, this was y-axis, and this is z-axis. This angle is theta. So to complete the circle, to complete the circuit, complete the loop, we have to move theta is equals to 0 to 2 pi. So I had z a cos theta plus j hat z a sin theta plus k square divided by root over of z square plus a square, say whole to the power 3 by 2, whole to the power 3 by 2 into d theta. Now if I integrate these terms, so I can find equals to mu 0 I divided by 2 into a square divided by z square plus a square whole to the power 3 and 3 into k hat. So what will be the direction of the magnetic field? What will be the direction of the magnetic field? The direction of the magnetic field is along k hat. So B function of z is equals to mu 0 I by 2 into a square divided by z square plus a square whole to the power 3 and 3 into k hat. This is the magnetic field at an axial point for a closed current forming a circular loop I. Now, as I have given my title of the lecture, that the concept of magnetic dipole. Here you can remember from electrostatic that the for an electric dipole, the field at an end-on position is due to a dipole is E is equals to 2p divided by 4 pi epsilon 0 z cube. What is P? P is the dipole moment. P is the dipole moment. Now, if I want to compare, if I want to convert, rather I want to convert this expression of electrostatic to magnetostatic, I already told in my lecture on magnetic field, introduction to magnetic field, mu 0 by 4 pi in magnetostatics is equivalent to 1 by 4 pi epsilon 0. So if I replace this on B, then what would happen? B function of Z is equals to, I am just repeating again, mu 0 I by 2 a square divided by a square plus z square whole to the power 3 by 2 into k hat. So I am writing this expression as mu 0 by 4 pi mu 0 by 4 pi into I into 2 into pi a square divided by a square plus z square whole to the power 3 by 2 into k hat. Now, if a very less than z, that is the dimension of the loop, is very less than uh, z in comparison to the distance of the field point, so I can write this expression as mu 0 by 4 pi into 2 into I into pi a square by z cube into k hat. Now compare this term with electric field E is equals to 2p by 4 pi epsilon 0 z cube into k hat in case of electrostatic. Now you can see everything is the same. mu 0 by 4 pi is equivalent to 1 by 4 pi epsilon 0. Z cube is also here. K hat is also here. 2 is also here. So I can write in electrostatic P is equivalent to the term I into pi square. We denote it as M. This is called magnetic dipole. Magnetic dipole. So what is magnetic dipole? So what is magnetic dipole? Actually, magnetic dipole is a current into area, that is I into pi square. So what is the direction? Since dipole is a vector quantity, dipole is a vector, so what is the direction of this vector? The direction of this vector can be is along which the current is flowing. In this case, in our case, the current is flowing along anti-clockwise direction, so the dipole moment will be upward to the paper, that is along k hat in our case. So magnetic field in our case, magnetic dipole moment M in our case is I into pi square into k hat. Remember that this expression is quite general. Don't think that we have calculated it for a circular loop. So what will be the case for any other loop? So for any other loop, say it may be square, say I, this will be equals to a square. If all the sides are a, so it will be a square into I into say k hat. Magnetic dipole M is equals to a square a into k hat. Thus from the from the expression of magnetic field due to a circular loop along the axial position, we can have or we can get the concept of magnetic dipole, which is a very important quantity in magnetostatic. So thank you. I hope you have enjoyed my lecture. Thank you for hearing me.